Okay, I thought I would go over the components on the cart motor in greater detail. Most of the stuff is getting switched over to the box motor, and I want to document it properly. So this is one of the coils opened up on the cart motor. There were 12 of these. They have a quad filer coil on them, 3 power wires and a trigger wire. There are 3 number 18 wire 65 feet long and 1 number 24 wire on for the trigger right there. And then this key system is basically the resistance for each chip in the circuit. Each coil is modular. They're self-contained. You only have a power wire, a ground, and then the energy return wire, which is right here, that the energy is recaptured into the second battery bank, and that's tied to the positive of the whole system, and that's tied together. So it's a basic Bedini SG circuit, only there's three of these circuits in this configuration. I use 6 diodes, the 007 diodes. I use 6 for each chip. The chips are NPN chips, 160 volt at 14 amps, I think, 14 or 15 amps. So it's kind of a look at the back of one of these opened up. So turn it around here. So as you can see, I use these little connectors to hold the chips. Now you're not going to get a large chip in that type of connector. You could probably find one that'll work as well. And then the transformer plates as the core, and there's a piece of polycarbonate, and it's all taped together, and then you put screws through that, and that holds the whole coil assembly together. So that's basically how the coil is set up. Now the batteries, there's 2 banks of batteries. There's 6 batteries in each bank. These are telecom batteries like they use in a cell phone tower, the backup batteries from a cell phone tower. They're rated at 44 amp hours apiece. And you could use car batteries, but these batteries are sealed batteries, so I don't have to worry about any hydrogen leaking out of the batteries. They're designed for close quarters inside of a small building where the cell tower's next to, so there's not a risk of the hydrogen leaking out. So there's 6 batteries, and the batteries are grouped in parallel in 2 subgroups of 3 batteries. So what I have here is the A bank by itself. There are 3 batteries in the subgroup. They run down to a circuit breaker, and there are 6 batteries in the A bank, and there are 2 breakers rated at 20 amps at 12 volts, like a car circuit breaker. And I just split it up because obviously a 40 amp breaker would have done the same thing, but in this case they're tied in 2 subgroups because of some of the experiments I was doing. I thought it would be a good idea. Never used it, but anyway, that's the way it's set up. So because there's 6 of these, there's 276 amp hours in each bank. There's an A bank and a B bank, and you can see the bank slides on a drawer, so you can see it doesn't move easy, but it does slide in and out. So there are 2 banks like that. That was a shelf in the back of a tech truck I had, so I used it to create the shelves. Now you wouldn't have to have the thing slide in and out, but it is definitely a lot easier to work on for that fact. It's a little heavy, and when you pull it out too far, you risk the thing toppling over, so I have to be real careful, but it did help some. So this is basically just a breakout panel. Let me wire things up in different configurations. So I'll go through this real quick for you, and we'll look at the other side of this. So basically you have an inverter, and what happens in this case, the A bank is connected to the inverter. So the power runs from the A bank into the inverter, through the inverter, where it comes out 120 volts. And then it runs up into a bridge rectifier. I just build my own bridge rectifiers. They're nothing but diodes anyway. So the signal is 120 volts AC, and it's rectified into 120 volts DC. Passes out of that, and this is for the generator to connect to the same line, and right now there's no other wires hooked to these two leads for AC. So basically the line travels down into the capacitors. There's 3 capacitors, 150 volts at 8,700 microfarads. They're in parallel, which creates 26,100 microfarads. And after they pass through the capacitors, they run to the switch. The switch, well actually I'm sorry, they run through the meter. They run through the amp meter and then to the switch. So the switch is after it's rectified, after it's run through the capacitors. This is an important fact, because the switch, when you turn that off, the capacitors stay charged. And if you've tried to pump up 3 large capacitors with a inverter, you'll know what I'm talking about. If you drain them off, they're a little harder to charge up from being discharged. So basically I shut them off so there's no live current running through the wiring on the outside of the motor. Now when it's all engaged, you know, these things are hot at 120 volts. All those things there are dangerous. If you touch them, they're live. So you wouldn't want to mess with that. But in this case, that's a feature that helps me better manage the capacitors. This is why it was done that way. So, and the power runs out of the capacitors to the leads here, which run around the outside of the motor. As you can see, there's a hot, a positive, a negative, and a return. Now the negative wire really didn't need to be this big. I used AC house wiring. I think it's number 10. So it's fairly large. A stranded wire would have been better. That's what John Bedini uses. So, you know, I take his word as the gospel. So basically it would have been a better idea. Current flows around the outside of here, and then these lugs, each coil is modular, so they're hooked into these lugs, and you can see here how they're tied in to the lugs. So that's how it runs. And then when the coil fires, when each one of these coils fire, they fire sequentially. They're grouped in a subgroup. 3 coils fire almost at the same time, and there's 3 groups of 3 coils. So they're positioned around it. The only problem I really had with this design was the other side of the coil was not secure. So when it got to a certain speed, the resonance of the device caused the coils to oscillate slightly, and it caused it to vibrate. Once you got above that speed, it was fine, but the box motor overcomes these issues that I had. So basically the coil fires, and then it runs down the return, back over from the return. Now that's coming in at 120 volts DC, that's pulsed, so that could go up to 1,000 volt spikes, easy. The spikes run through this amp meter right here, out of the amp meter to a loop that gives me a digital amp meter. Just a little redundant way for me to check that that meter's close to being right, basically. So out of the amp meter, and then it runs back in to the wall here where it's tied to. There's two capacitors at 20 volts at 98,000 microfarads or 196,000 microfarads. They're running in parallel. So comes out of those capacitors and then runs back out. It's tied in here and it's bridged, and then the coil runs back to the B bank, and then that runs down into the second bank of batteries. So that's kind of how it's set up. These are magnets are from a wind style PMG generator. There's 16 of them, and they're pretty strong magnets, so a little hard to get apart. The other magnets I was running were N52 144 magnets, 144 pound pulling pounds. These weren't rated that way, but they are definitely stronger than the 144s. If anybody has any questions about this, I'll be glad to tell you anything I can. I'm not trying to keep anything a secret. Everything I'm doing is completely being published. And now some of it may be overlooked only because it's a lot to keep track of, people. So if I miss something and I don't give you something and you need it, please just email me, leave me a message on Facebook. I'll try to answer your question. So I'm going to give this a push. You can see 1.45 amps at 120 volts. And that's the voltage, 121 volts. So the output's 12 amps. Now as it speeds up, it'll get up around 3.5 amps top, but it's unloaded, so the faster it goes, the more amperage it draws because the gate's staying open longer. So that gives you any idea.